Another type of problem that's a little bit crazy in form is the old ancient discussional problem about hands moving on a clock. In this case, we have the second hand, the ones that reads the seconds, that goes around, one time every 60 seconds. As it's moving from 12 down to 4, what is the rate that it's moving as it passes the 4? So the question reads, at what rate is the distance between the tip of the second hand and the 12 o'clock mark changing when the second hand passes the point to 4 o'clock? So how fast is this distance changing as the second hand moves when it hits the 4? So what I have here is that the second hand I gave as r for a circle as radius, and I do have an angle created here that the second hand is creating as it spins around. And I want the distance between these two. Not a circular distance changing, but the straight distance. Now, what I'm asking for is dx dt. Okay, now a couple things I look at this. One, the second hand, or what I call r, is a constant. The radius does not change as it flows around the clock. Two, the angle here does change. So I need to find out what that angle is at that particular point. So what I need to do is create an equation that has this picture in mind as I look at it. And the picture that does it creates the equation of the law of cosines. C squared equals a squared plus b squared minus 2ac, or 2ab, cosine of the angle. So whatever these two sides are here is what the two are here. So I'll read that again. C squared equals a squared plus b squared minus 2ab cosine theta. Well, in this case, my a and b sides here and here are the same thing. So I'm not worried about that. So here is x squared equals r squared plus r squared minus 2r squared cosine theta. Now I've got some stuff to fill in here before I take the actual derivative. First, there's 360 degrees in a full circle and 60 seconds to go around in that circle, which reduces to 6 degrees every single second. So this hand, every tick of a second, moves a 6-degree value. In radians, that's pi over 30, just converting degrees into radians here. So at 20 seconds, which is the time it takes to go from here to here, at 20 seconds of time frame, to get to the 4 mark, the angle is 20 times these 6 degrees, or 20 times these pi over 30s, which means the angle would be 120 degrees, or 2 pi over 3. So now I know my angle value when it hits the 4 mark. This angle is 120 degrees, or it's 2 pi over 3. Next, here's my equation as it is. If I take this equation and plug in 120, I can find my x length at that point. So r squared and r squared, again, they don't give us a size clock, so we're going to keep that blank. Put in 120, cosine of 120, or 2 pi over 3, is negative 1/2, which means the x length is the square root of 3 times the size of the radius. So no matter what size clock you have here, give me the radius. When it moves past the 4, this x length will be the square root of 3 times that radius length. So now looking at this equation, I have the angle, radius is a constant, and I now have the x length at 4. Let's jump to the second page. Now it's time to take the derivative of that equation and see what I get. As I take that derivative, I get 2x dx dt is equal to 2r dr dt plus 2r dr dt minus, now this is the quotient rule here, so I got to go ahead and use the quotient rule. First, times the derivative of cosine, which is negative sine, d theta dt, plus cosine, the second, times the derivative of the first. Now this looks really, really complicated. But one thing that's nice about it is since our radius is a constant length, The derivative of a constant is 0. So that means this is 0, and this is 0, and this is 0. So all we're left with is this equation. 2x dx dt is equal to the positive of this. Or in other words, if I get dx dt by itself, the rate at which the length is changing, this is the equation I am dealing with. All right? That was the original question. How is the distance between the 12 and the 4 for the second hand changing when it passes the 4? This is all I need to find. Now, again, what I found on the previous page is that r is a constant. They didn't give me the radius length, but it would be a constant. The angle at 4 was 2 pi over 3, or 120 degrees. And the rate at which it was changing at that point is pi over 30. It's a constant change. Every second moves the angle to pi over 3 radians every value. So that's the rate at which the angle is changing. And from the previous page, we found that x at that moment when it passes the 4 is r square root of 3. Fill each value in, and here's the rate at which it's changing. It's changing pi over 6, the size of the radius, for every second. Pi over 60, size of the radius, for every second. This is a difficult problem. Please take your time looking at this. Any questions, don't be afraid to ask, but this is a challenging related rates problem.